So, good afternoon to all of you. So, today is the second lecture on functional materials. The first lecture was, if you remember, on materials for catalysis. So, from today onwards, we'll start on energy materials, particularly materials for batteries and supercapacitors. So, today's lecture will be mostly on battery materials. But before that, we will have a little bit of idea about what electrochemistry is and why we require batteries and stuff. Okay, the overview of the content of today's lectures, just let me run past it. So one is basic electrochemistry. So we will revive your knowledge on whatever you know about electrochemistry. This will be followed by what batteries are, what do you mean by primary and secondary batteries. Then we will discuss what do you mean by some common terms which is normally used in with respect to battery and energy storage, which is energy versus power density. We will discuss a little bit on lithium-ion batteries and then the components and processes which take place in batteries. And we will talk a little bit on cathode materials for LIB. So this is going to be the overview of content, whatever we are having today. So coming to what we exactly talk about electrochemistry. So when we talk about electrochemistry, it is good to know a little bit of history of the electrochemistry. So the story of electrochemistry, it begins with Alexander Volta, the famous scientist who announced the invention of the voltaic pile, and this was in 1800, which is basically the genesis of all the modern electric battery we see. So what Volta did is he used two metals, and the pile was built using zinc and copper, and he alternated the discs of these opposing metals with a pasteboard or a cloth which was dampened with a solution of water and salt or vinegar. And then an electrochemical reaction happened in each of these three disc unit of the pile, and it formed an electric cell, and which was generating a current. Therefore, by changing the number of the units, Volta could increase or decrease the amount of electricity which could be produced. So this is the first known example of something which is an electrical battery. But that was then. And after that, the application of this was kind of brought into the notice by William Nicholson and Anthony Carlisle. And they used the voltaic pile to split water into its basic components, which is hydrogen and oxygen. And this achievement actually ushered in an entirely new branch of science, which is known as electrochemistry, which we all now know as electrochemistry. So what were the landmark achievements before we actually go into what these batteries are and how we do electrochemical energy storage? So the fact is that, there are a few landmark achievements which happened in this field. So first and foremost was the laws of electrolysis, which was brought forward by Michael Faraday, which was in 1833 to 1836. So he found out the laws of electrolysis. Followed by this, the Daniell cell, which was invented by John Frederick Daniell, and this was in 1836. Then the fuel cell, which was by William Robert Grove in 1842. Then we had the lead acid battery, which we use even today, which forms the workhorse of many, many different applications. So that was by Gaston Plant, and it was in 1859. Then the electrolytic production of aluminium, that was a very important thing at that particular point of time, which was in 1886. And this was by Charles Martin Hall and Paul Herold. And after that came in the use of alternating current to drive induction motor. This was by Nikola Tesla in 1887. Then the dependence of reaction rates on temperature and general interpretation of the thermodynamics of electrochemical process. This was brought in by Arrhenius and Nernst, the famous Nernst equation, 1889. Then Cottrell found in the Cottrell equation, which rules the relation between electrode kinetics and the mass transport by diffusion, which forms the cornerstone in developing any kind of material which is going to be used in electrochemical energy storage. So that was in 1903. And then the nickel and iron battery, which was brought forward by Thomas Edison, which was in 1914. So this we can say kind of gives you in a nutshell all the landmark achievements in the field of electrochemistry, which happened in the early 20th century. So what exactly is electrochemistry? So electrochemistry we can define as a discipline that deals with the chemical reactions that involve an exchange of electric charges between two substances. So the chemical change is going to produce an electric current and vice versa. So electrochemistry is basically the study of reactions in which charged particles like ions or electrons, they will cross the interface between two phases of matter, typically a metallic phase, which is the electrode, and a conductive solution, which is the electrolyte. So what you have is an oxidant which takes in an electron and it gives you a product. So this particular reaction is the reduction reaction, electron gain. So oxidation number is decreasing. The other process, you have a reductant and you are undergoing an oxidation process. You are getting a product with the release of electrons. So here electrons are lost. So the oxidation number is going to increase for the precursor, whatever you're using. So this is in nutshell the idea of electrochemistry. So now when we move into this electrochemical energy storage, there are a few terms which we will be using quite often. So some definitions you should remember. When we talk about something which is an electrode, so we have two kinds of electrodes. One is the anode and the cathode. So what is the anode? Anode, if you remember, is the negative electrode of a cell, and it is associated with oxidative chemical reactions that releases electrons into the external circuit. On the other hand side, what you have is the cathode, which is the positive electrode of a cell, and it is associated with reductive chemical reactions that gains electrons from the external circuit. Then you have active mass. When we talk about these materials, that electrode and cathode materials, you have something which is known as active mass. So what is this active mass? It is that particular portion of the material which is generating the electric current by means of a chemical reaction within the battery. So when you fabricate an electrode, it is not only the active material you're using, you use some kind of binder, you use some conductive agents, you have a current collector behind it, and you are spreading it on the collector. This entire thing is known as an electrode. But when you talk about active mass, it is basically that material which is generating the electric current by means of chemical reaction within the battery. So this is a very important concept which you should remember. Then of course, between the anode and the cathode, you need something which should be conducting the ions, and this role is played by the electrolyte. So it is a material that provides pure ionic conductivity between the positive and the negative electrodes of a cell. And now to have a physical barrier, because otherwise you will have shorting of the entire device. So this is a separator which is there, which is the physical barrier between the positive and negative electrodes, which is incorporated into most cell designs to prevent electrical shorting. So this separator can be a gelled electrolyte or a microporous plastic film or other porous inert materials which is filled with the electrolyte. And separators, please remember, it must be permeable to the ions and it should be inert in the battery environment. So it shouldn't be reacting with anything in the battery environment. It should be as inert as possible and it should allow the movement of the ions. So these are some basic definitions which you should remember before we start talking anything about batteries. Now some basic concepts. So those were the basic definitions. Now you come to some basic concepts which you should kind of have in your mind. You should be ready in your mind before we move into further deeper into the subject. So one is this known as the electroneutrality principle. So as the name suggests, what is this? Electroneutrality means bulk matter. It cannot have a chemically significant imbalance of positive and negative ions. So if you are dissoluting a particular metal in solution, it will proceed to a measurable extent only if some means is provided for removing the excess negative charge that remains. So this is done by using an electron acceptor ions in the solution or by drawing the electrons out of the metal through an external circuit. So only when you remove these excess negative charge, then only the dissolution of a metal is going to continue spontaneously and to a measurable extent. So this is the electroneutrality principle, because bulk matter cannot have a chemically significant imbalance of positive and negative ions. Now there is another important term which is interfacial potential. Now interfacial potential, as the name suggests, so there are interfaces. So that means this is going to exist at all the phase boundaries. So in case you have a metal or a metal electrode which is in contact with an electrolyte solution, the interfacial region will consist of an electric double layer. And the potential difference between a metal and the solution is almost entirely located across this very thin double layer, and it leads to extremely large potential gradients in this particular region. So this is a interfacial potential. So what is the electrode potential? So when we look into, see, this is particularly, so when you are moving at as the distance from the surface of this electrode, now in both in A and in B, you will find that the gray part is given as electrode. In one of them, you will find on the surface you have an excess of negative charge, and now you are having a solution over here. So as the distance from the surface of the electrode increases, the concentration of the cations or anions decreases, and it gradually becomes equal to the concentration of a solution. So as a result, the electrical double layer is formed. So over here, as you can see, you have an electrical double layer. Why? Because over here you have a concentrated negative charge, and so from the solution, all the positive charge is going and accumulating over here. So what you see in this yellow line is nothing but the potential. So you see there is a very high potential in this very small area. So while this electric double layer is formed, the potential difference between the electrode surface, which is the phi 0, and the solution at a distance x, whatever is the distance x, is called the electrode potential. So this electrode potential is nothing but the difference in potential from the surface of this electrode to a finite distance in the solution. So similarly, as you see over here, here the potential is kind of increasing, and here you see the potential is again increasing, but in the other direction, because over here now you have the positive charge. Okay, so you should remember there are two regions over here from the surface of the electrode. One is this region 1 and the other is the region 2. So what is this region 1? It is the dense part of this electrical double layer, or which is also known as the Helmholtz or the Stern layer. And 2 is the diffusion part of this particular electrical double layer. So this is the concept of electrode potential, which you should understand. Now coming to what is known as the very simple cell, I'm sure all of you have heard about it, because right at your 11th and 12th you have all read about the voltaic cell. So motion of electrons in ionic bonding, it is used to generate an electric current, and a device which is constructed to do this is nothing but a voltaic cell. So what you have? Two electrodes which are made of different materials, both of which are chemically reacting with the electrolyte in some form of ionic bonding. And at the end, what you have is some kind of charge movement over here, and this is nothing but a voltaic cell. So voltaic or galvanic cells, so what happens? So spontaneous reactions, they occur in the galvanic or the voltaic cell. So if you talk about a Daniell cell, as I said, if you remember the landmark achievements, we spoke about the Daniell cell. So Daniell cell is using a zinc electrode, which is the anode, and a copper electrode, which is the cathode. So you see zinc is getting zinc is basically dissolving in the electrolyte, and what you're getting is zinc ion and electrons are released, whereas in the copper case, what is happening? Copper ions are basically taking in this electrons, and what it is forming is basically a copper, solid copper, metal copper. So the flow of the electrons is happening from the anode to the cathode. So ultimately how this looks like, so you have two different metals which is connected by a salt bridge or individual half cells which is separated by a porous membrane, and what you see on the outside is basically when you connect this you will find a voltage being generated on this. So this is known as a voltaic cell or a galvanic cell. Please remember, spontaneous reactions, they occur in the galvanic cells. So when we talk about this, obviously we need to know something about the cell potential. So what is cell potential? Cell potential is a measure of how well a cell reaction can push or pull the electrons through a particular circuit. And the electrical energy which is generated by this spontaneous reaction is proportional to the cell potential. So now, of course, you know this E0 cell is nothing but E0 cathode minus E0 anode. So it is the difference between the cathode potential and the anode potential. And how will you get this E0 value? It is from this change in the Gibbs free energy. So delta G is equal to minus NF E0. So delta G0 is the change in the Gibbs free energy. N is the number of moles of electrons. F, you know, is the Faraday constant, which is given as 96,500 coulombs per mole. This is a more roundabout figure. And the E0 cell is the standard cell potential. So this is how you get the cell potential. Now, something which you have to remember when I talk about that in voltaic cell or galvanic cell, what you have is spontaneous reaction. So what exactly is the spontaneous reaction? This depends on the placement of your particular metal as per their reduction potential. So the more negative the reduction potential is, the more readily the element is going to act as a reducing agent. That is, it itself is going to get oxidized. So if we look into this particular entire series over here, as you move down from top to bottom over here, you are getting more and more of the reducing power of this particular material is increasing. So you are comparing this with respect to the standard hydrogen electrode. Okay, all these potential are with respect to the standard hydrogen electrode. And what is a standard hydrogen electrode? So when hydrogen gas is adsorbed at 1 atmosphere pressure over a platinum electrode, which is dipped at 25 degrees centigrade in 1 molar HCl as shown over here, it is a regular electrode of hydrogen and its potential is considered to be 0 volt. So all these reduction potentials, whatever you see, is compared to the standard hydrogen electrode. So this is a reference electrode and all other electrode potentials are referred to it. Now coming to a very important equation, as I told you, Nernst developed these particular equations. So this is a Nernst equation which shows you the relationship between Gibbs free energy and equilibrium constant. So delta G0 you all know is equal to minus RTL and K, and delta G for a reaction is dependent on the concentration. So this is delta G0, which is basically the standard state condition, the steady state condition, whereas when I am having this delta G, it is for this particular delta G is going to depend on the concentration. So how it is going to depend? So delta G is delta G0 plus RTL and Q is the reaction quotient. So it is the concentration of the product over concentration of the reactant. So using this equation and your equation that delta G is equal to NF E cell minus NF E cell, so you will get, if you substitute it, you will get your E cell or the cell potential, which is the cell potential E0 E naught cell minus RT by NF ln and this is nothing but your Nernst equation. So now coming to electrolytic cells, we had already talked about the Daniell cell or the voltaic cell, in which case you have a spontaneous reaction. In electrolytic cells, what we have is the non-spontaneous reaction which happens. So electrolysis reaction, this will require electrical energy to induce the reaction. It is not going to happen spontaneously. So if you have molten NaCl, if you're electrolyzing it to form liquid sodium and chlorine gas, this is one of the reactions. It is not going to happen spontaneously, and you are going to add in some electrical energy from some battery or something, and you're going to push this reaction to happen, and that is why this is known as a non-spontaneous reaction. So the concept of reversing the direction of the spontaneous reaction in a galvanic cell through the input of electricity is the heart of the idea of electrolysis. So though the direction, please remember one important thing over here, that though the direction of the electron flow in electrolytic cells may be reversed from the direction of spontaneous electron flow in galvanic cells, the definition of cathode and anode remains exactly the same. Always remember that reduction will take place at the cathode and oxidation occurs at the anode, no matter whichever sign you are considering, whether it's a voltaic cell or whether you are considering an electrolytic cell. So cathode and anode definition is the same. Reduction will take place at the cathode and oxidation will take place at the anode. So now let's compare a galvanic and an electrolytic cell. So in case of a galvanic cell, what you see over here is that spontaneously what you are seeing over here, in case of the galvanic cell, copper is spontaneously plated onto the copper cathode in the galvanic cell. Okay, so over here the copper is going to be spontaneously plated on the copper cathode. But whenever you have an electrolytic cell, it is going to be the other way which the reaction is going to happen. So over here you see that E naught cell is positive. It is 0.78 volts. So that means obviously your delta G value is negative. So this is a spontaneous reaction. Whereas if you are doing the other way around, in this case the E naught cell is negative. So delta G is positive. So that means this is definitely not a spontaneous reaction. You have to apply, you have to give in some energy for this particular reaction to happen. Okay. So what is Faraday's law? Faraday's law will give you that the amount of substance consumed or produced at one of the electrodes in an electrolyte cell is directly proportional to the amount of electricity that passes through the cell. So by definition, 1 coulomb of charge is transferred when 1 ampere current is flowing for 1 second. So this is the equation, which is the Faraday's law equation, where W is the mass of the substance, M over here is the molecular weight of the substance, I is the amount of current you are passing, T is the time for which the current is passed, N is the number of electrons which is transferred, and F is the Faraday constant. Here I have given the actual value, which is 96475. In the previous slide, it was given as roundabout value 96500. So the amount of chemical change you have to understand is proportional to the amount of current passed. So this is the Faraday's law. So what are the various variables in an electrochemical cell? So you see there are so many things which varies. So you see the external variables. So there is temperature, there is pressure, there is time. Then there are various electrical variables. The potential you can change, current is changing, quantity of electricity which is passed is being changed. So there are a lot of solution variables also, bulk concentration of electroactive species, concentration of other species, electrolyte, and concentration of other species You have to see what is the electrolyte concentration, what is the pH, the solvent, and then you have various electrode variables. What is the material you are using? What is the surface area of your electrode? What is the geometry of your electrode? What is the surface condition? And then you have various mass transfer variables like mode, whether it is a diffusion mode, it is the transport of the ions are happening in a diffusion mode or in a convection mode. Then the surface concentration, then adsorption. So many different variables are there in electrochemical cells. So obviously you can understand it's not so straightforward. So now you see where these different processes are taking place. So you have an electrode on the left hand side and the bulk solution is there at the extreme right. So what happens over here is right near the electrode, you will find all this electron transfer taking place. And then you have this the desorption process from where you are having all these chemical reactions and the mass transfer is happening and it is reaching the bulk. And also you can have this other way around. It can also occur in the other way around where, from the bulk it is moving to the surface and from the surface it is getting adsorbed and it is coming over here. So these are all the different variables in the electrode region, in the electrode surface region, as well as in the bulk solution, where all these different processes are taking place and they have lot of variables in it. So one very common term which we'll use in electrochemistry is overpotential. So what is a potential? You have some potential which you have theoretically calculated, but many a times you will see that if you're applying that much amount of potential, your reaction doesn't take place. So the extra potential which must be applied to an electrode to initiate the electrode reaction in an electrochemical cell, that is basically the overpotential. So it is the difference between the equilibrium potential E and the applied potential EJ required to initiate the electrode reactions, and this is what is known exactly as the overpotential, which is given as delta E. So it is EJ minus E, which is the difference between the applied potential and the equilibrium potential. So there are various things which contribute to this cell overpotential. So what are they? The most common ones are the ohmic drop, the activation overpotential, and the diffusion overpotential. So what is ohmic drop? So ohmic drop, it develops in the electrodes because of the fact that the electrolyte solution, it has a finite conductivity. Okay, so that is why it is not that it can conduct everything. So it has a very finite conductivity, and that is why when you see on the electrodes, you will find that ohmic drop is happening. So it always occurs between the working electrode and the reference electrode because your electrolyte solution is having a finite conductivity, and this contribution to polarization is equal to current into the resistance, with so current density and the R is the resistance. So this is equal to IR. So this is the ohmic drop, whatever. See, this gives rise to an overpotential. Then you have something which is known as the activation overpotential. Why? Because this happens in one or both electrodes because there is a kinetic inhibition of one of the steps involved in the electrode reaction. Maybe dissolution of the reactive ion or chemisorption of the reaction product. If you remember the previous slide, so there were many processes which were happening. So if any one of the process a little bit is inhibited, in that case what you will find is this activation overpotential. So this activation polarization, it occurs because there's a slow electrode reaction, and the reaction at the electrode, it will require an activation energy in order to proceed, and that is why it is known as an activation overpotential. Then you have something which is known as the diffusion overpotential. So now you have generated all these ions and all. So this happens because, and then these ions also need to move. So how the problem is going to be? Because at one or both electrodes, due to the presence of all these concentration gradients, which is there in the vicinity of the electrode surface, as I told you, the concentration of the ions is much more at the electrode surface vicinity. So there is going to be a difference in the concentration on the electrode vicinity and at a distance from the electrode. So that basically is giving you the diffusion overpotential. So as a result of electrochemical reaction, the concentration at the electrode surface no longer have their equilibrium values. So if the migration through this electric double layer is very rapid, then diffusion from the bulk of the solution towards the electrode will be unable to replenish the ions at the double layer quickly enough. And so what you're going to have is a concentration gradient. Okay, so this is the reason why you see a diffusion overpotential. So now coming to what batteries are. So far what we have discussed is basically your all the different terminologies, this was more or less the refreshing part. We were refreshing your knowledge about electrochemistry and a few terms, and then some battery related terms, and then a little bit about your in electrochemical, the terminology which is normally used in electrochemistry. So now what we will discuss is your batteries. So what is a battery? A battery is a device that converts chemical energy directly to electrical energy. Okay, that is the very plain definition of battery. You have some chemical thing stored in that battery, which has been made in a way where you have electrodes and electrolyte and stuff, and then you are kind of using their battery to discharge, that entire energy stored in the form of chemical energy, and when you discharge it, it is changing into or converting into electrical energy. So battery consists of one or more voltaic cells, and each voltaic cell, it consists of two half cells which is connected in series via conducting electrolyte. So a battery's voltage output and current rating, they are determined by the elements which are used for the electrodes, then the size of the electrodes and the type of electrolyte used. And depending on type, cells typically have a nominal voltage potential anywhere between 1.2 volts to 3 volts, depending on the battery chemistry, depending on its size, depending on the electrolyte used. You will have these kind of nominal voltages which will range anywhere between 1 to 3 volts. So batteries, you must understand there are two different types. One is primary batteries, the other is secondary batteries. What is a primary battery? Primary battery is one where you have a cell reaction. Once that cell reaction is done and you have converted to electrical energy, you cannot reverse the cell reaction back. So basically it's a one-time use. So those batteries are for one-time use, and this is known as a primary cell or a primary battery. Whereas in case of a secondary cell or a storage cell, you can recharge it. How do you recharge it? So basically the chemical energy, whatever was converted in electrical energy, again when you charge that particular cell, what will happen is it will again the reaction is going to get reversed and is going to get back into its original form, and it will store that electrical energy as chemical energy, so that when you discharge it once again, it will again change that chemical energy to electrical energy. So basically this is a rechargeable cell. Now, sometimes what we use something known as dry cells. So please remember the dry cells, they have a moist electrolyte which cannot be spilled. And there is also something which is known as sealed rechargeable cells. These are secondary cells that contain a sealed electrolyte that cannot be refilled. So remember that in case of primary batteries, we sometimes have something which is known as dry cell, which has a moist electrolyte and not a liquid electrolyte. So the spillage part is very less. That way, when we say that that battery has lost it's in the end of life, and then it starts oozing out a liquid. So that is mostly that electrolyte, which is what is there. In case of dry cells, we have a moist electrolyte, so there is no spillage. And sometimes for rechargeable cells also, we have sealed rechargeable cells. So they contain a sealed electrolyte, so you cannot refill the electrolyte once again. So it is sealed. So what are the common types of primary cells? So you find that something that is known as a carbon zinc tricell. You have also alkaline cells. You have zinc chloride cells, you have mercury cells, and also silver oxide cells. Out of this, the mercury cells are typically now phased out because mercury is extremely toxic and nobody wants to use it. So mercury cells are getting phased out. So what you have in the market as primary cells are mostly carbon zinc tricelles. You have alkaline cells, you have zinc chloride cells, and you also have silver oxide cells. So what is a dry cell battery? So over here, if you see, you have a carbon positive electrode, so which is the cathode. You have an electrolyte paste over here. You have a separator. And then in the electrolyte, you have a carbon and manganese dioxide mixture. And the negative electrode is basically made of zinc. So if you have this battery and you're connecting it to a light bulb, what you see is the bulb is getting lighted up, and this is kind of batteries which you see when we are using an electrical torch and stuff like that. So this is the common type of carbon zinc tricells, where carbon is acting as the cathode and zinc is acting as the anode, and your the electrolyte is basically carbon and manganese dioxide mixture. Then you have another type of primary cell which is known as an alkaline cell. Now this over here, you see over here, this is basically the different kind of cells, and they have a particular name attached to it. Like one is the 4.5 volt, this is 3LR12. Then you have a D-type cell over here, you have a C-type cell depending on the dimensions. So these dimensions are fixed. So if somebody says this a D-type cell is being used, so you know the fixed dimension of the cell which is being used. Like C-type cell, then you have AA batteries, you have AAA batteries, you have quadruple A batteries, you have 823 batteries, which are kind of 12-volt ones, then you have 9-volt batteries, then you have these kind of coin cells, which are basically normally used for lithium-ion batteries. These are CR2032, these are 3-volt cells, and you also have LR44 batteries. So these are all the different dimensions of the standard, the cells which are found in the market. So the alkaline cell are generally for AA, C, and D type. It has around 1.5 volt output, and it is same as carbon zinc cells, but they are longer lasting. So it consists of a zinc anode and a manganese dioxide cathode in an alkaline electrolyte. If you remember in the previous case, the electrolyte was different. So over here you have an alkaline electrolyte, which is potassium hydroxide. And this works with high efficiency even with continuous use due to its very low internal resistance. So for the if you see this carbon zinc dry cells, in this case, what happens? The performance of the cell is better with intermittent operation, whereas when you have alkaline cells, they work better with continuous use. So another type of primary cell is the zinc chloride cell, and this cell is also referred to as a heavy duty type of battery. It is a modern zinc carbon cell, and it has a very little chance of liquid leakage because the cell consumes water along with the chemically active materials. So what happens is, because it consumes water, but the type of reaction whatever it has over there, that zinc chloride takes in the water, forming a zinc chloride oxyhydride. And that is the reason why what happens is that liquid electrolyte whatever is there, it gradually it turns into solid. So by the time at the end of the cell life, what happens is this becomes totally dry. So that leakage probability is less with the zinc chloride cells. Okay. Then of course I talked about mercury cells. So this has a zinc anode and a mercury compound cathode and potassium or sodium hydroxide electrolyte. But obviously this is becoming obsolete due to the hazards which are associated with proper disposal of mercury, and nobody wants to use a toxic material. And that is the reason why mercury cells are getting discontinued. Then we have something which is a silver oxide cell. So what you have over here is a zinc anode, a silver oxide cathode, and potassium or sodium hydroxide electrolyte. So this is typically available as a 1.5 volt miniature button form. So these silver oxide cells are what you will find in hearing aids, in cameras, in watches, that small miniature button form cells, whatever you're using is the silver oxide cell, where you're having a zinc anode and a silver oxide cathode. Next comes the first instance of the rechargeable batteries. So among the rechargeable batteries, the one which we'll be discussing a little bit is the lead acid wet cell. And this is one of the most widely applied type of secondary cell, which is extensively used in vehicles and other applications requiring high values of load current. Definitely this occupies a lot of space because the energy density of this battery is not very high. So obviously you cannot use it for any portable applications, but it has a lot of applications if you are trying to use it for renewable energy storage. And obviously you are also using in vehicles, all these different kinds of vehicles which we have. The battery which is used is the lead acid battery. So in this case, the positive electrode is made of lead peroxide and the negative electrode is made of spongy lead metal. The electrolyte is sulfuric acid. The output is about 2.1 volts per cell. And what you do is, to increase the voltage, what you will do is generally use it in a series combination of either 3 of these lead acid cells put together or 6 of them put together. So the ultimate output voltage is either going to be 6 volt or it is going to be a 12 volt. So that is the lead acid wet cell. Okay. So then how this particular electrode reaction looks like. So while discharge, what is happening? The lead and the lead dioxide is reacting with the sulfuric acid and it is leading to the formation of lead sulfate and water. Whereas, so ultimately as your discharge, so you have this charge cell, and when you are discharging, what happens is you are resulting in the formation of lead sulfate and water. When you are charging this particular cell, as I said, this is rechargeable. So again, this particular electrode reaction can be reversed. So when you are recharging this particular cell, the lead sulfate will react with the water and it will again go back and form that lead dioxide and sulfuric acid. So this is what is going to be there. So what happens is, suppose we have a lead acid battery and it is discharged to some extent. So how do you know what is the state of discharge of this particular battery or the state of charge of the battery? So you will measure it with the specific gravity. You will measure the specific gravity of this particular lead acid cell and you will find out that what extent it has been discharged. Why? Because there is water. So when it is getting discharged, it is forming water. So that water is there. So the specific gravity of the material, it changes. And so by checking the specific gravity of the electrolyte, you should be able to make out that how much of the percentage of this battery has already discharged. So the current rating of this battery is given by how much discharge current they can supply for a specified amount of time, and the unit is generally ampere hours, and this rating is proportional to the physical size of the lead acid battery. So specific gravity, is a ratio that compares the weight of a substance with weight of water. The state of discharge, how much charge the battery has left, is checked by measuring the specific gravity of the electrolyte. So as the cell discharges, more water is formed, lowering the specific gravity of the electrolyte. And so you get to know whether this battery is charged or it is discharged, how much of it is discharged. Now there is one more point you have to understand, that in all this lead acid battery, that lead sulfate which is formed, how long you can leave that lead sulfate just like that? If you are totally discharging that particular battery and then you're leaving it for a very long time without charging it once again, it is very difficult to recharge that battery. What happens is that lead sulfide deposition starts happening, and lead sulfate deposition starts happening, and then what happens, due to osmolar ripening, you will get big crystals of lead sulfate getting deposited, and then it is very difficult for you to apply charging and then to dissolve that lead sulfate again with water and reverse the reaction. So it is very important that there is a continuous charge and discharging cycle of this lead acid wet cell happens, because if you are not doing that, then you are leading to an early degradation of that particular battery. Okay, so so the charging of an automobile battery. So what you are going to do, as the cell so what you will have is this particular reaction is going to take place. So from lead sulfate and water, this is going to react when you're charging the battery, and it is going to give rise to lead oxide, and you are going to generate the sulfuric acid. So the next rechargeable battery we'll talk about is the nickel cadmium cell. Now this type of a cell, it delivers high current and it can be recharged many times, and it can also be stored for long periods of time. So the applications include portable power tools, alarm systems, and portable radio and TV equipment. So what is the reaction happening? You have nickel hydroxide and you have cadmium. So when you are discharging, you are forming nickel hydroxide and cadmium hydroxide. Whereas when the charging of this material happens, you have nickel hydroxide and cadmium reforming. The electrolyte in this case, please remember, is potassium hydroxide, but it is not taking part in the reaction. What the only function of potassium hydroxide in this case is to conduct the ions basically, and so the transfer of the hydroxyl ions, whatever is there, so that is the only purpose of potassium hydroxide over here, as the electrolyte itself is not taking part in the reaction. So that is why for these particular cells, there is no change in the specific gravity with the state of charge. Whereas in case of the lead acid wet cell, there was a change in the specific gravity with the state of charge. For the nickel cadmium cells, because your electrolyte is not taking part in the reaction, you will not find any change in the specific gravity. Then of course, why nickel metal hydride? Nickel cadmium cell anyway was good enough, but then the biggest drawback of the nickel cadmium cell is the use of cadmium, which is a bit toxic. So obviously you need something which cannot, if you're using these kind of rechargeable batteries, a lot of applications are there. So if you're using it, then definitely disposal of the cadmium which is again, it's not very, it's not environmentally benign. So you need to look for environmentally benign options, and that is why nickel metal hydride cells were developed. So this is used in applications demanding very long running battery performance for high-end portable electrical or electronic products like power tools, and they offer 40% more capacity over a comparably sized nickel cadmium cell. It contains the same components as nickel cadmium cell, of course, except for the negative electrode, which is instead of cadmium, you're having a metal hydride. It's a little bit more expensive than the nickel cadmium cells, and the drawback of this is it self-discharges more rapidly, and so that is why it cannot be cycled as frequently as the nickel cadmium cell. So you can see for a nickel metal hydride, the material is almost the same. You do have nickel hydroxide, but instead of cadmium, what you're having over here is a metal hydride, which is being used in place of cadmium. More capacity, but the problem is that there is a lot of self-discharge, and secondly, it's more expensive than the nickel cadmium cell. So now when we talk about cells, and then from the cell we are joining it together, we form a battery. Please remember that if you need more amount of voltage, you will be connecting the cells in series. If you need more amount of current, then you will be joining these particular cells parallel to each other. And for a battery pack, if you have a particular voltage and current output in mind, then you will be having these various type of series parallel combinations. And this combination of cells is called a battery. So you can connect three batteries in this way, and ultimately you will get a higher voltage. And so the voltage, whatever is there in the battery, and then when it is passing through a particular resistance, the load, whatever you give, it will determine the current which this particular battery is going to generate. Okay, so if you want something for which you want the same voltage 1.5 volt, but you want a higher current output, in that particular case, what you're going to do is you are going to connect all these particular cells parallel to each other, and you will get a particular higher current, as you can see over here. So to provide a higher output voltage and more current capacity, cells are generally connected in the series and parallel connection. So this is how generally it is whenever we talk about batteries and the cells, and this is how we show. This is the circuit diagram for a particular battery which is connected in parallel to each other, and this is the entire circuit diagram when there is an external load which is applied. And please remember, the actual amount of current which is produced when the battery is connected to a load resistance is equal to the load which is connected. So the same thing, if you are having a voltage of 1.5 volt and the load keeps on changing from 7.5 ohm to 150 ohm to 2.5 ohm, you will find the current which is generated keeps on changing. So current drain, it will depend on the load resistance, whatever you are adding to the battery. So now why this so much of importance is given to battery? So please understand, in our first lecture, as I had discussed earlier, that we are trying to cut down on fossil fuels, obviously because of the entire heating effect or the greenhouse gas effect, whatever we are seeing, which is kind of increasing the temperature of our of Earth, and that is the reason why we are looking to cut down our dependence on fossil fuels. So we have to use more and more renewable energy, and if you are using more and more renewable energy in the form of wind or solar or geothermal, so what happens is for the wind and solar particularly, which are the ones which are mostly used, the supply is not consistent. Whereas whenever you are having your in your homes or in the industry, whenever you require electricity, you need a constant supply. So you cannot put into the grid sometimes, the constant availability of energy is not there. So sometimes during the peak summer and during when the sunshine is very high, that time you will get a lot of solar power being generated, but that time probably the grid doesn't need it. So you need to store that excess amount during the night time when there is no solar power being generated, but the utility is very high at that time, then that stored power has to be put into the grid. So how do you store that? So that renewable energy needs to be stored, and this is where basically this entire battery concept becomes very, very important. Okay. So you have all these different storage techniques where you will be using it for this renewable energy storage. So harvest and conversion of sustainable clean energy, including solar energy, wind, mechanical vibration, and waste heat. Energy storage typically is in the form of chemical potential, including batteries, hydrogens, and biofuels, and management and efficient usage of energy, including smart buildings and efficient lighting systems. So this is basically the entire energy management system or energy utilization chain. And that is why batteries are becoming more and more important. Then again, another very important thing is that in the transportation, whatever we are using is basically your fossil fuels. Most of the transportation demands as of now is still met by fossil fuels, and that again is increasing the carbon load. So if you are having so much amount of carbon load, then it is not good. So what you have to do is you have to kind of shift to more and more electric vehicles. So for electric vehicles also what you need is very good high energy density battery system. So that is also one of the prime reasons why battery storage is getting more and more important. So EVs, they have a superior technology and it has a reduced operational and maintenance cost compared to the internal combustion EV engines, which are the hybrid engines. So benefits of EVs are a lot, but the only problem is that how you can improve the energy density of these batteries. So here a small brief history of these EVs is given. So if you see, the first successful electric vehicle made its debut in 1890. So that time it was these lead acid cells which were being used, for this electric vehicles. But afterwards, what happened is by 1997, Toyota, it introduced the Prius hybrid. And 2006, Tesla began producing all electric sports car. And obviously now, in the market, we are getting all these commercial EVs, which has come into the picture. So now you have to understand that there are various kinds of batteries which have been used since this EVs have come in since 1890. You had lead acid batteries being used. You also had nickel metal hydride batteries being used. But currently what we are looking into is lithium ion batteries. Why? Because in all the previous two technologies, the energy density cannot be increased beyond a further point. Whereas lithium ion batteries are now the fastest growing battery system because it has a high energy density compared to all the other battery types. And lithium itself is extremely lightweight, so obviously the energy density is very high. And somewhere we are now hovering near the 200 watt hour per kg level, 265 watt hour per kg level. And maintenance definitely is there, no maintenance requirements compared to the others, but lithium based batteries, they are continuing to improve. And also you see the cost parity which is happening compared to the internal conversion based EV engines. So you see over here right now, previously in 2016, 48% of your car price was actually battery price. Whereas by 2030, it will be somewhere around 18%. So currently we are hovering at 27 to 24% is the battery price compared to your car price, the entire car price in various models. Whereas by 2030, probably it is going to come down to around 18%. So this is the EV cost parity. So obviously batteries have a lot of applications, and this has been kind of vetted by the Nobel Prize Committee. And in 2019, the Nobel Prize was given to these three famous professors, Professor John B. Goodenough, Professor Stanley Whittingham, and Professor Akira Yoshino. And this was because of their pioneering development, which they did in the field of lithium-ion batteries, which is being used in all the portable devices which we use now, including our mobiles and all the other things. And we know how important mobiles have become, and this wouldn't have been possible if the lithium-ion batteries were not developed. So lithium-ion batteries having application in portable electronics, lithium-ion batteries having application in renewable energy storage, it is having application in electric vehicles. So you can imagine the importance of lithium-ion battery technology. And that is why Nobel Foundation in 2019, the Nobel Prize was given to these three professors. And this was the reason why, because as the Nobel Foundation puts it, this lightweight, rechargeable and powerful battery is now used in everything from mobile phones to laptops and electric vehicles. It can also store significant amounts of energy from solar and wind power, making possible a fossil fuel-free society. So that was the application for which it was awarded the Nobel Prize. And by 2030, this lithium-ion battery supply chain is from the mining to fabricating the battery to its use, to its recycling, to its again use. So this entire supply chain is going to go up to a $400 billion market by 2030. So as more and more gigafactories will be emerging all over the world for this. So how does this lithium-ion battery work? So please understand this. So one is you have an anode, which is at a low voltage and at a high chemical potential. The cathode, which is going to be at a high voltage and a low chemical potential. You have a separator, you have an electrolyte, and basically what is happening is the lithium ion is moving. So when you are charging the battery, it is moving from the cathode to the anode, and when you are discharging the battery, that is when you are connecting it to an external load, the lithium ion is going to move back from the anode, which was stored in the anode. It is going to move back and it is going to come back into the cathode. So this is basically the idea of a lithium ion battery. So what was the contribution of these three scientists? So one was Professor Stan Whittingham. So what he did early on is that he used a lithium metal anode, and this was way back in 1976. This was the paper which was published, for which he got the Nobel Prize, journal, and of course the work after that in Journal of Electrochemical Chemistry, Electrochemical Society in 1976. So you are using your anode as a lithium metal. For the cathode, you had titanium disulfide. And then what you are doing is, when you are charging and discharging, what you see is that from this lithium metal anode, the lithium ion is moving and it is getting into this titanium sulfide layered structure. And when you are again charging the material, it is again going and it is moving back to the anode. This lithium ions are moving back to the anode. So this is what he saw, and his first attempt worked. But the major problem was that as you continue this charge and discharge cycle, so it is rechargeable obviously. So when you are charging, you're getting something, discharging, you're getting something, and charging, you're getting the same material back. But when you continue with the cycling process, what happened is he found that the lithium basically anode, it started depositing in such a way that lithium whiskers were being formed, and that whiskers started growing, because this is shown, like as if it is a very big thing, but you can imagine the coins, they are very, very thin. So what is happening is that lithium whiskers are getting developed, and it is kind of perforating through this particular separator, and it is going and touching the cathode, and if that happens, then there is a short circuit, and obviously this is not going to work. So this was the biggest problem, and this caused the battery to explode. So application wise it was not good, but conceptually he showed for the first time that lithium ion can move as charging, with charging and discharging, and we can have a kind of a battery which is made with this kind of material. So after this, what was the contribution of Professor John Goodenough? In 1980, John Woodruff, he saw this work which was done by Professor Whittingham, and what he did is he had a very genius idea. He understood that the major problem why this kind of this titanium, the voltage was very low, and it is not giving a higher voltage, is that because you are using sulfides. So instead of sulfides, if you move into oxides, then obviously the voltage is going to increase, because this depends on where the energy levels are for a sulfide, sulfur to S2 minus and O to O2 minus. So where these energy levels lie, as a chemist he could visualize that, and he understood that to improve the voltage, which is ultimately going to improve the energy density of a battery, instead of sulfides which are again unstable, it is much better to use the oxides. So what he did is, he, instead of using titanium disulfide, what he used is lithium cobalt oxide. So LCO he used as a cathode, and lithium metal was used as an anode, and ultimately he could improve the voltage of this particular cell to almost 3 volts. So this was an improvement which he did compared to that of Professor Whittingham, and this particular cathode material was so good that it still, even today, it is used in most of the commercial lithium ion batteries. And then, of course, with that also, the problem of the formation of this lithium dendrites or whiskers remained, and so cyclability was an issue. So then that time in Japan, Professor Akiro Yoshino, he was working on various carbonaceous materials, and he knew that carbon has a tendency of intercalating lithium inside it. And so what he used is, he used a carbonaceous material as anode, and he repeated the cathode which was taken by Professor Goodenough, and this he did in 1984, 1986 and 1986. And so he had an LCO cathode, a carbonaceous material as anode, and lithium could be with charging and discharging. It was able to move between the cathode and anode. The cyclability improved remarkably, because now there was not much of a problem with the lithium dendrite formation. And so basically, this was basically the birth of the lithium ion battery. So in 1991, the lithium-ion battery was commercialized by Sony and Asahi Kasei Corporation, with Samsung SDI beginning the manufacturing of the lithium-ion batteries at their Korea plant in 2000. So this was the contribution for which the Nobel Prize was given. So this was a schematic representation of a lithium-ion battery. So what you have is the LCO material, LiCO2, and then you have over here, which is the graphite material. So lithium ions, which are shown as these yellow balls, they are kind of moving from the cathode to the anode when that charging is happening, and when you are discharging this, the lithium ion which is stored in this carbon planes, so that is getting again shifted back into the cathode structure. So this is the way the lithium ion battery functions. So the electrolyte is going to be ion conducting. It will not conduct electrons. The electrons have to move in the outer circuit. So that is why you are having an electrolyte which is ion conducting, a membrane over here, a separator which is ion conducting, whereas the electrons will move in the outer circuit. So this is how charging and discharging, and the lithium ion keeps on shuffling between the cathode and the anode. So what are the common related to the batteries? One is power capacity. So this is the energy that gets stored in a battery, and it is measured in watt-hour. Then you have something which is known as power capability. What is power capability? So maximum amount of current that a battery is capable of delivering, and it is also termed as C rating. A C rating of a battery is very important. If you are charging and discharging a battery at a higher C rate, what you will find, you see that the capacity of the battery is decreasing. Then you have something which is known as a nominal voltage. So since the voltage of the battery stays constant and is not variable, it is known as nominal voltage. So it's a fixed voltage. Then you have something which is a charging current. So maximum amount of current which can be applied to the battery for charging it. Then charging voltage, again the maximum amount of voltage that must be applied to the battery to charge it efficiently. So these are some of the common terms which are related to batteries. Then you have something which is known as the discharging current. So it is the maximum amount of current that can be drawn out of the battery and delivered to load. If the current drawn, you exceed this particular whatever, this current, then what is going to happen? The battery is going to drain up very fast, and since it drains very fast, it will heat up, and if it heats up, then it might also explode. So that is why you have to keep a very sharp tab on the discharging current. Then shelf life. Shelf life, sometimes if your battery is staying idle or it is sealed and it's staying on the shelf for a very long span, especially in the shops, what happens is that they continue to self discharge. So what happens is that it can stay powered up and usable only up to a certain level. If it self discharges itself to a very high extent, then obviously what happens, you cannot use that battery, and this is more important in case of a non-rechargeable or a primary battery. If you are having a primary battery where the cell reaction can be converted to electrical energy only once, and when you are storing it on the shelf, it is continuing to self discharge without connecting to a load, then in that case, after a particular point of time, the battery is no longer usable. This is definitely not a big problem in case of rechargeable batteries, because again you can connect it to some external device and you can power it up and you can charge the battery once again. So shelf life is a big problem in case of a primary battery, though not that much in case of a rechargeable one. Then you have something which is known as a cutoff voltage. So the voltage for which the battery might get considered as completely discharged is the cutoff voltage. If you try to discharge the battery after that voltage, it can get damaged. And then there is something which is known as cycle life. So if a battery is completely charged and you discharge it to 80% of its original capacity, then it is said to have complete a cycle. So the number of cycles that a battery completes is defined as a cycle life. If the cycle life is more, the battery definitely has a better quality. So when do you say that a rechargeable battery itself has reached its end of life? Does a rechargeable battery means you can continue charging and discharging lifelong? No, it is not like that, because there is going to be internal resistance and you will lose some of the capacity. So if you continuously charge and discharge a battery, after a lot of use, you'll find that what happens is that you cannot use that battery efficiently. And that is a prime example of it is your mobile batteries. You see, you are buying your mobile, it comes with a battery, and then after 2 to 3 years, normally you'll find that you have to change the battery because it is not working. Why? Because anyway, it was a rechargeable battery. So according to what we are saying, this chemical reaction can be infinitely, it can be charged and discharged, but that doesn't happen. It does lose its capacity, and then when we see that the original capacity what you had, that goes down, that after charging also, no matter how much you charge, it doesn't go to beyond 80% of the original capacity, then we say that the battery has reached its end of life. Okay, and then it's the time for you to change that battery. So please remember the cycle life concept of the battery. Now you have something which is known as a Ragone plot. You will be hearing about this quite a lot when you talk about various energy storage technologies. What are the different energy storage technologies? You have batteries, you have supercapacitors, you have fuel cells, so all these things. So this is a plot which is used for comparing the energy density of various energy storage devices. So what you will be having over here is basically power density, as you can see on the x-axis, and this is a logarithmic scale. And then you have energy density in watt hour per kg, which is again on the y-axis, and what you have over here is again the logarithmic scale. So over here you see all these different energy storage technologies are given, and wherever it is placed, it shows the energy density and the power density. So if you look into aluminum electrolytic capacitor, it is sitting right at the bottom right corner. So that means it has a very high power density, but the energy density is very low, which is the case in case of capacitors. They will give you huge bursts of power, but the capacity of the energy density is very low. Whereas if you look into fuel cells, what you will find is the energy density is very high, but the power density is extremely low. Whereas you have in aluminum electrolytic capacitors, what you see is that the power density is very high. Almost comparably, you will find the power density in case of ultra capacitors, but the energy density of ultra capacitors is much more. So that is why we'll discuss a little bit about ultra capacitors in the coming lectures. And then you have all these various battery technologies. So you see the lead acid battery, nickel cadmium battery, lithium battery. So what you see over here is that the power density in case of lead acid battery is much, much less compared to that of nickel cadmium, and that is also less compared to lithium batteries. So lithium ion batteries have good power density compared to these batteries, and also it has a little higher energy density compared to all these batteries. So definitely this is one of the good technologies which we have. So this is the concept of the Ragone plot. So the amount of time in hours during which a device can be operated at its rated power is given as the ratio between the specific energy and the specific power. So you see over here in all these lines, some time is given over here. So you can see that for the lithium ion battery, it is lying in this 1 hour line. Whereas when you have these capacitors, it is lying in milliseconds. So the amount of time for which it can deliver that energy, this is given in all these slanting lines, whatever you can see. Because this is the amount of time in hours during which a device can be operated at its rated power. And it is given as the ratio between the specific energy and the specific power. So by the placement of these various storage technologies in the Ragone plot, you can find out that which is going to be the most useful for whatever application you are planning to use it. So now we speak about a lot of voltage of the battery. So what do you mean by voltage of a battery? So cell voltage, please remember we have many places where this term voltage is coming. So what is cell voltage? Cell voltage is determined by the compatibility of the whole system. So you have the anode, you have the cathode, you have the electrolyte, everything is having a potential associated with it. Anode has a potential, cathode has a potential. Cell voltage is basically the compatibility of this whole system. So in particular, the difference in the chemical potential of the anode and the cathode, this is termed as the working voltage, and this is also known as the open circuit voltage. So this open circuit voltage is the difference in the chemical potential of the anode and the cathode, and this is divided by the magnitude of the electronic charge, and this gives you VOC. Now, the difference in the Gibbs free energy for the reaction between the charge state and the discharge state of a battery is given by this delta GR, which is nothing but your thermodynamic equation, delta H minus T delta SR. And this delta H you can represent as delta U plus P delta V. So at the end of the day, what you have is this delta G or Gibbs free energy is dependent on the change in the volume and the change in this particular entropy. So if you look into these changes, this has already been established that they are very negligible. So if you look into the order of the changes, it is 10 to the power minus 5 to 10 to the power minus 2 electron volts. So they are very negligible. So ultimately this delta G value is dependent on the change in this internal energy. Okay. So that is the one which is grossly affecting the change in the Gibbs free energy between the charged and the discharged state. The chemical potential is related to the partial molar quantity of this Gibbs free energy. So the equilibrium voltage, if you see the equilibrium voltage Ex, it is obtained by this particular equation, minus delta G by F. F is the Faraday constant, and Xj minus Xi is the solid solubility limit of the intercalation reaction. So what is intercalating? Your lithium. So the solid solubility limit of this lithium intercalation reaction, which is given by Xj and Xi, this is going to ultimately give you the equilibrium voltage of the battery. So now please remember something, that when we talk about this voltage of a battery, the voltage is very important. So when we talk about energy density of a battery, how you define energy density? Energy density is basically a product of your the working voltage of the battery and the specific capacity of the battery. So that means if I can improve the working voltage of a battery, in turn, I am improving the energy density of a battery. So I can, and how this working voltage I can increase? By increasing the difference between the chemical potential of the anode and the cathode. So if I take a cathode which is going to be having a very high potential, an anode which is having a low potential, And if I can increase the chemical potential of the cathode, in that case, I should be able to get a very high voltage, and so my energy density is going to increase. But realistically, that is not possible. Why? Because there is something which is known as the electrolyte, which is sitting between the anode and the cathode. And here it has a very important role to play. So what is this role which it is playing? So you see over here that your electrolyte is basically having a difference between the HOMO and the LUMO levels. Okay, your electrolyte has a HOMO and LUMO level, and the chemical potential of the anode and the cathode, it has to be selected in such a way that the chemical potential of the anode, it will lie below the lowest unoccupied molecular orbital of your electrolyte, and the chemical potential of the cathode is going to be located above the HOMO, so which is the highest occupied molecular orbital. So you are limited by this. So if you are having something where the mu A is lying above the LUMO, then what is going to happen? The degradation of the electrolyte is going to happen. Your anode material is also going to degrade, and ultimately your material or the battery is not going to be stable at all. So after a few cycles, your battery is going to degrade, and the cyclability of the battery is going to be very, very poor. So you are limited by this. So it is not that you don't have the cathode materials or the anode materials which are not at higher chemical potential and lower chemical potential. You can have it, but the problem is, the limiting factor is the electrolyte. Most of the electrolytes will decompose when you are having something, if the mu C value of the cathode is much lower than what you are seeing over here. So ultimately, anytime when we are using this anode and cathode, a little amount of the electrolyte does degrade, and this leads to the formation of something which is known as a solid electrolyte interface film, or an SEI film. And this is a passivating layer which is formed on the anodes. Cathode also has it, but the extent to which it is formed on the cathode is much less compared to the extent in which it is formed on the anode. So this SEI plays a very critical role in the anode part of your battery. You have to understand this is a kind of a the problem over here is the SEI definitely will degrade a part of your electrolyte. So your efficiency is never going to be 100%. But the SEI plays a very important role. Once it is formed, it should actually form a passivating layer. And this layer has a very beautiful property. It will permit the diffusion of the lithium ions through the film under a uniform electric field. It will reduce the overpotential and the concentration polarization. It will also prevent the aggregation of the electrochemically active particles and will maintain a uniform chemical composition at the electrodes. So the formation of this SEI, it effectively prevents the exfoliation of graphite during the insertion and the extraction of lithium ions. So when you're having that carbon anode over there, the graphite anode, so if you're forming that SEI, it will prevent the exfoliation of the graphite. So it is going to preserve the integrity of the anode structure. But you must understand that the SEI film, it increases the internal resistance of the battery and consumes part of the lithium ions from the cathode, and so it will lead to both power and capacity loss. So you need to have an SEI because that will form a passivating layer and is going to prevent further dissolution of your electrolyte in the anode. But on the same time, the thing is that if it is too thick, then this is going to be a big problem because you are using up more amount of the lithium, and that is not getting back again. So that means your efficiency is lower. But if you are not having an SEI, then in that case, the electrolyte is continuously going to eat up your anode material. And so then the materials, the battery material stability is going to be critically affected. So this is the SEI formation pros and cons. So as I said, I had discussed theoretical capacity of the electrode materials. So this corresponds to the number of reactive electrons and the molar weight of the designed materials. So when I talk about theoretical capacity of electrode materials, it is given by this formula, NF by 3.6 into M. N is the number of electrons which is transferred. In case of a lithium ion battery or a sodium ion battery, this N is 1 because it is 1 electron transfer. F is the Faraday constant, and this M is the molar weight of the material. So you can understand that you can improve the specific capacity by increasing the N or by decreasing the M. So in case of lithium ion battery, what we are having is this N is fixed. So that M factor, if you can have a lighter and lighter material, in that case, the capacity is going to increase. And but the energy density, as I said, is a product of the specific capacity and the working voltage. Specific capacity is dependent on these two factors. Working voltage, I have already explained to you that working voltage critically depends on the electrolytic homolumo window. So you can increase the chemical potential of your anode and decrease the chemical potential of your cathode as much as possible. But the problem is that your electrolyte should be able to support it. And right now the bottleneck is in the electrolyte. We are not having too many electrolytes which can work in a very high window between where the difference between the anode potential and cathode potential, chemical potential, is very high. So what are the elements which are available for the design of new electrode materials? So as I said in the previous slide, lighter elements are favored as electrode materials. Why? Because of their higher specific capacity, as are most elements in the first 4 periods of the periodic table over here. So the advantages of transition metal oxides as cathode materials are incomparable. Why? Because they have a variable valence state. Variable valence state which facilitates more electron storing sites. Furthermore, the electronegativity and ionization energies determine the type of bonds between the transition metal ions and the ligands, and they also play a critical role in improving or bringing down the specific capacity of your material. So the major points which you have to consider whenever you are looking to design new electrode materials are natural abundance, how much it is naturally abundant, lack of competition with other industrial applications, eco-friendly nature for processing, usage and recycle, and low cost. So technologically, the electrode materials must offer a large reversible storage capacity at the desired electrochemical potential. So please remember, metallic lithium anode has a very high theoretical capacity of 3,850 milliampere hour per gram. And silicon reaches a value of around 4,200 milliampere hour per gram if the final alloying compound is Li22Si4. In case of lithium, the compound which is in case of lithium, as such, only lithium when you act as an anode, that is why the theoretical capacity is very high. But whenever we are changing that lithium anode to a graphite anode, in that case, the theoretical capacity immediately drops down to almost 372 milliampere hour per gram. It doesn't go beyond that. But the positive aspect of this is that though we get a lower capacity, theoretical capacity, the energy density is a little less. But the biggest advantage of it is that the recyclability of the cyclability of the cell is very high, because here you don't get the formation of this lithium ion viscous, which can cause short circuit and it can cause your cell to explode, as well as cause degradation of the material, which is not there. So that is the reason why, though the research is like how you can use this metal lithium anode so that you can improve the theoretical capacity. But as of now, for the commercial cells, what we use is a graphite anode. So what are the factors which will affect the electrochemical potential of the electrodes? So one is the electronegativity. What is electronegativity? It is the tendency of an atom or a functional group to attract electrons or the energy density towards itself. So a larger difference in the electronegativity predicts the formation of a more ionic bond, whereas if there is a smaller difference, what you form is a covalent bond. Please remember that metals with more ionic bonds, they form more dense structures, whereas those with more covalent bonds will form a poorly packed structure. So this structure density, it influences the crystal and the phase stability of the material, and it also influences the specific site energy of lithium ion. So where the lithium ion is sitting, that also has a site energy associated with it. So the more amount of energy you need to pull out that lithium ion or push that back in, that will kind of increase or decrease your electrochemical potential. So that means electronegativity affects the electrochemical potential of the material. Then another very important factor is we are using these different transition metals, and transition metals has varied amounts of these d electrons. So there is a relationship between the electrode potential and the number of electrons in the d orbitals in the transition ions. So in general, the potential will increase with increasing number of electrons in the d orbitals. Why? Because more amount of energy is released when electrons are inserted into orbitals, or more amount of energy which is consumed when electrons are promoted from orbitals, the higher is going to be the electrochemical potential of the electrode material. So you can see over here that nickel 4 plus is a D6 system, cobalt 4 plus, which is so it is a D5 system. So in all these cases, you see over here, it is the potential is given on the y-axis and the number of d electrons are given in the x-axis. So you can see very easily over here that when you are moving to cobalt, cobalt is having a very high potential, and obviously because the voltage is very high over here, then obviously the energy density of your resultant cell or the battery is going to be much higher. Whereas nickel also, if you see, nickel also has a very high potential, but nickel has some other problems which we will be discussing later on. So what you find over here is that when actually Professor Goodenough proposed this lithium cobalt oxide in his lab, that time all different studies were done using all these different transition metal ions, and it was found that lithium cobalt oxide was the most suitable candidate, obviously because of the potential which it was giving, and then it was gradually correlated to the number of d electrons these particular transition metal ions are having. Then another very important thing is the specific capacity which you get out. So if you plot the potential versus the specific capacity in milliampere hour per gram, you come to see a very nice conclusion. You see over here, this inside this green circle, what you have is vanadium, chromium, iron, manganese, cobalt, and nickel, all going from 2 plus to 3 plus state. So the oxidation state change is the same over here, but you look into the potential as given in the previous slide, from vanadium to chromium to iron to manganese to cobalt and nickel. When you are increasing in the same oxidation state, the number of d electrons is increasing, and what you find over here that the potential is also increasing. And but in this case, the specific capacity of the material is more or less in the same region, though the potential is increasing, but the specific capacity stays unchanged. Whereas if you look into your bismuth 4 plus 5 plus and molybdenum 4 plus 5 plus state over here, what you see over here, the potential is definitely high for bismuth 4 plus 5 plus. Why? Because because bismuth is belonging to period 6 and group 5 of the periodic table. It has a large atomic number and large electronegativity, and this definitely leads to a larger electrochemical potential. But the gravimetric capacity of this material is less compared to molybdenum, because bismuth, the weight is much more compared to that of molybdenum. And that is the reason why when you have the specific capacity of molybdenum 4 plus 5 plus compared with that of bismuth 4 plus 5 plus, the gravimetric capacity is high, whereas the potential is high in this case. So all these factors you have to consider when you are actually finding out or you're exploring new materials for your electrodes. Then another important role which has to be taken into account is the counter anion. The counter anion, as you see in the previous slide also, all of these were, all these ions, the counter anion was the same, and that is why you could compare it. They were all phosphates. Okay, so all these ions, whatever it is, the counter anion was a phosphate. And you see over here what is happening in case of these copper, chromium and all, cobalt and all these things, all the material over here, the gravimetric capacity is around 600 watt hour per kg. Whereas if you are moving on to more and more of the cobalt and the nickel side, you are getting a higher gravimetric capacity of 800 watt hour per kg. So similarly over there, because all was phosphate, similarly you can have different types of counter anions. So what are the different types of counter anions you can think of? You can have silicates, you can have phosphates, you can have molybdates, you can have tungstates, you can have sulfates. So what role does it play? So if we see LiFeSiO4, and if I consider the phosphate salt of the same cations, that is lithium ion, so you have LiFePO4. Now look into the potential over here. So if this, in this particular plot, on the x-axis we are having electronegativity, on the y-axis we are having potential. So you are having lithium ion silicate, the potential is 2.7 volt, whereas in case of lithium iron phosphate, the potential you see is increasing. It is 3.45 volt. And that means what? That means the working voltage has increased. Your working voltage has increased means what? Your energy density of the cell is going to increase. So this is how you will find out that when you are moving from a phosphate to a molybdate to a sulfate, in case of this Li3Fe2 systems, you'll find that the lithium ferrous sulfate, it has a high potential of around 3.6 volt, and it has very high electronegativity. Why? Because this counter anions, they have very high inductive effect, so that is going to give rise to a lot of electronegativity. And electronegativity is more means then your ionic the bond strength is going to be more, and if that is the case, in that case what is going to happen, the electrochemical potential is going to be more of these groups. So what is the ultimate idea of this, all these, after going through all these different factors which are affecting the electrochemical potential of electrodes? So selecting elements is the first step, wherein the atomic weight, abundance, environmental impact, and the cost, they are to be considered. And then you have to see the electronegativity of the elements and the counter ions. This is another key parameter that determines the electrochemical potential of the electrode materials. So whenever you are designing materials for electrodes, these are the key considerations which you have to keep in your mind, that how I can design new electrode materials for better performing batteries, whether it is lithium or it is sodium or whatever. So with this, we'll end the class today. If there is any question, you can ask. So if there are no questions, then we are ending the class today. You all have a nice day. Thank you.